Hey folks, so this video lesson is going to be the conclusion of circular motion, looking specifically at the force that is acting when an object is in circular motion. So to begin here, the definition of this force, it is going to be a centripetal force. Note the spelling there, note how it's pronounced, centripetal force. That force is going to be pulling the object in towards the middle or pushing the object in towards the center of the circle. Just like with a centripetal acceleration, where that is a center-seeking acceleration, a centripetal force is going to be a center-seeking force. So by definition, again, based on forces and accelerations, the direction of the net force has to match the direction of the acceleration. So for an object in circular motion, the net force is going to be that centripetal force, which is going to cause that centripetal acceleration. Now we can still find this with a simple mass times acceleration, but now it's that specific centripetal acceleration that we're talking about here. Looking at the diagram on the right-hand side, you'll see the person swinging this ball in a horizontal circle, right? Because this is an overhead view of what that would look like. So the inertial path that it is talking about and the momentum of the object, that is matching where the tangential velocity is. So that green vector indicating the momentum being the product of mass and velocity, is going to be in line, and it's going to be in the same direction as that tangential velocity. That's where the mass is trying to go, but it is being pulled inward by this individual holding onto it via some cord, and the force that they are exerting is towards the center. So as the object spins, this person is pulling the object inward, but because of its velocity and because of how it is connected to that rope or whatever it may be, it continues to turn in a circle. So because the centripetal force is acting at 90 degrees with the actual straight line path, that tangential velocity of the object moving in the circle, that's what causes the curvature. Think back to projectile motion. The force pulling on it was vertical. That horizontal velocity stayed constant, so we saw that parabolic curve. Same idea applies here. The force being center-seeking is at 90 degrees. It is perpendicular to the tangential velocity of the object moving in the circle. That perpendicular relationship between the force and the velocity is what causes that circle to be created. So again, our centripetal force is that force that is going towards the center that is causing it to accelerate towards the center of the circle. Now, when you're driving on a curve, the common thought is that, well, but I turn, so I feel myself being pushed outwards, right? Well, why are you feeling like you're getting pushed outward? And that's where the term centrifugal force comes in. The centrifugal force is not what is causing the motion that you experience. It's not why you feel like you're being pushed outward. The centripetal force is still what's acting, except now, based on the way that you're moving and as you go to turn, your mass is trying to maintain a straight line path, but the object around you is turning. So when you're in a vehicle that takes a sharp turn and you feel yourself being thrown outwards, I'm going to use quotes there, to the side of the vehicle, you're not being thrown outwards. The vehicle is turning and your mass is still going straight, causing there to be a collision. So that centripetal force, again, at each one of these locations is pulling inward. Your motion is attempting to go in a straight line. So your mass here is represented by those yellow dots, which are going to be going tangent to the circle when you enter that curve. So as the vehicle begins to turn. You're trying to go straight. The force is pulling inward on you, and that is what causes you to feel like you're being tossed outward when in reality, the vehicle turns and you don't. So you're moving in a straight line, the vehicle turns, that's why you feel that pressure outward on the side. It's because of the inertia. Remember, inertia is the property of an object proportional to its mass that resists a change in motion. Objects want to continue what they're doing until they're forced to change. In this case, the inertia of you, right, or whatever the object is that's moving, is moving in a straight line path. That vehicle turns, your mass still wants to move in a straight line until it physically can't anymore, right? And it's all because of that inertia. So we start seeing that turn. And eventually as you turn and then you straighten out, your mass is still moving in a straight line and you don't feel that pressure anymore. So the pressure isn't from you being thrown outward, it's from you moving straight and the object turning, which is forcing you to turn as well. Now the big thing here, force is still a mass times an acceleration. But now we're just adding one more type of force into our arsenal. This is going to be F sub c, right? That's centripetal force, as we would call it, which means the acceleration caused by the centripetal force will be A of c, the centripetal acceleration. So we still have a dependency on mass here. So the more mass the object has, that force is going to go up as long as our acceleration stays constant. So we're still going to see an inverse relationship between mass and acceleration according to Newton's second law of motion. Our concepts there still apply. They're just applied in a different context now. So mathematically, we have two different ways that we can go about finding this centripetal force. And each of them are going to be a derivation using F equals ma, where we can pull both of our formulas for the centripetal acceleration and multiply them each by mass. What we see are these two formulas here. Our two base formulas for centripetal acceleration were the tangential velocity squared over the radius and 4 pi squared times the radius divided by the square of the period. Well, now each one of those just has the mass component multiplied in. So we have mv squared over r, and we have 4 pi squared mr over t squared, where the mass has simply been multiplied in, which is going to allow us to take the product of mass and acceleration to get that centripetal force. These are two equally valid ways to get that centripetal force. Now, if you outright know the acceleration of the object, so if you know the centripetal acceleration and you know the mass, you can take the product of those two numbers and you don't have to go through these greater lengths if you already know what that quantity is. So we're going to take a quick look at an example here. And here we see a female hammer thrower using a 1.22 meter long chain to toss a 4 kilogram ball. If she completes one full rotation in 0.232 seconds, find the following: the velocity of the hammer as she releases it, the centripetal acceleration, and the tension in the chain. So first thing that we're going to do here is find the velocity of the hammer as she releases it. And we're going to write down all of our givens that we know first. So we know the radius is going to be 1.22 meters. We know the mass is going to be 4 kilograms. And we know the period of rotation t, right? The period is time per revolution. She completes one full rotation in 0.232 seconds. And that is her time for each individual rotation. Using those given values, we can solve for the velocity of the hammer as it's released. That is going to be the tangential velocity. So our tangential velocity, being 2 pi r divided by the period, gives us 2 times pi times our radius of 1.22 meters divided by the period of 0.232 seconds. So the tangential velocity that she is able to generate here is approximately 33 meters per second. Again, just using our formula for our tangential velocity is how we solve that one. Now for part B, the centripetal acceleration. So our centripetal acceleration formula, the one that I would advise using here, is the square of your tangential velocity divided by your radius, because we just found what that tangential velocity is. Now I'm going to record this on the screen as 3 sig figs. However, I'm going to use the full value from the calculator that I was given when I solved it out. So using that full numerical value, squaring it, and then dividing by our radius, we're going to get 895 meters per second, or meters per second squared. Now again, based on sig figs, that value is actually going to come out as 894.836, and there's some change there. So I'm going to use that full value again moving forward in part C, but to record the value as a response, I'm going to use 3 sig figs. The last question here is the tension in the chain. The tension in the chain is going to be the centripetal acceleration, because as the hammer thrower rotates, we're going to acknowledge that that tension is being generated by the force that she is applying, pulling in on that hammer as it rotates. So now our tension, which is a force that we're used to, is going to be equivalent to our centripetal force. So our tension being equivalent to our centripetal force is going to be our mass times our centripetal acceleration, which we just found in part B. So we get the mass, which is 4 kilograms, times the acceleration. Again, I am going to use the full value from the calculator, not the rounded value. And we are going to get, for that force, we're going to get 3,580 newtons using 3 sig figs. That's what we're going to see for our tension, which is going to be equivalent to our centripetal force. So there's a quick example where we can see our progression from tangential velocity to centripetal acceleration into a centripetal force, which in this case is equivalent to a different type of force. So this concludes our look at circular motion, starting with a tangential velocity, with the recognition that our velocity is going to be linear or tangent to the circle, and it's a straight line path that it is going to attempt to be moving in, which then brings us to our centripetal acceleration, which is a center-seeking acceleration, and then we have our centripetal force, which is our center-seeking force, where that force pulling inward on the object moving in a linear fashion is what is causing that curvature. Again, forces cause a change in motion. We have an object that is trying to move linear, but as it moves linear, it is being pulled at a 90-degree angle by that center-seeking force, and that force with that velocity being perpendicular to each other causes the curvature in the circle that we see. Thanks, folks.